Hello, welcome back. Here we are going into exponential equations. I am so excited about this section because there are many things in our world that expand exponentially. For example, population. They say technology doesn't go in a linear pattern, it explodes exponentially. So we're going to explore some of the stuff today about exponential functions and look at their graphs and how to solve it graphically. And then later we're going to get to logarithms so that you know every button on your calculator. You've been in school for, maybe 10, 11 years, and yet you have buttons on the calculator you have yet to discover. So that's what we're going to start today. So let's get started with exponential equations. You know what an exponent is? It goes into it's like a power. So an exponential function is a function that can be written in the form a times b to the x, and this time our variable is the exponent, and you may not have seen that before. A is called the initial value because if I put a 0 in for the x, anything to the 0 power is 1, so it would leave this constant out in the front. And b is called the base. So let's get some practice on identifying some of these exponential functions. Which of the following are exponential functions? For those that are, state the initial value and the base. Initial value, get in your head, that's when x equals 0 or time 0, the start. For those that are not exponential, or explain why they are not. So let's look at this first one, 5 to the x. We don't have something times 5 to the x, so our initial value is merely 1. If I put a 0 in for the x, I'd have 5 to the 0, which is 1. And the base, of course, is 5. That's what's being raised to the power. Let's look at this one. Y equals 6x to the negative 8. This is not an exponential function because your variable is not in the exponent. So this is not, the power is not a variable. So let's look at C, 4 times 2 to the pi. Again, this is not an exponential function because pi is not a variable. Pi is a constant. 3 times 7 to the opposite of x. This one definitely is a power function because your x is and your variable is in the exponent. It's a power. You also have a 3 times 7 to the opposite of x. Remember, you always do powers before you multiply. So you can't say this is 21 to the opposite of x. You cannot multiply these two numbers together. They have to stay separate. So the initial value is going to be 3, and your base is, of course, 7. 5 times 3.2 to the x. It is exponential because you have a variable for your power. Initial value would be negative 5. So there it is. Base is going to be 3.2. That's what's being raised to the power. To find the initial value, let x equal 0 and evaluate. That's what we just did with each of these. Notice that the initial value is always the constant, a. That's always the number out in front. Compute the exact value of the function for the given x value without using a calculator. So you're going to plug something in for x. So the function is 4 times 5 to the x power. So all we do is replace x with 0 and then use our order of operations. So we'd have 4 times 5 to the 0, and that would be 4 because 5 to the 0 is 1. Anything to the 0 power is 1, so we'd have 4 times 1. 6 times 2 to the x, and x is negative 3. So we'll replace the x with a negative 3. So we'd have 6 times 2 to the negative 3. Remember, when you have a negative power, that makes it go to the denominator. So it'd be 1 over 2 cubed, which gives us 1/8. So we'd have 6 times 1 over 8, which is going to be 6/8, or 3/4. Negative 4 times 5 to the x. X is 1/2. If x is a half, that's going to make this 5 to the 1/2 power. That's a square root. You can express a rational exponent as a square root, as a root, and the index would be 2. So it'd be negative 4 times the square root of 5, and you would leave it like that. So that's all there is to that section. All you're doing is plugging in values for x. This one, you want to find the exponential function whose values are given the table. Now this might look complicated, but it is not. It's easy peasy. All we have to do is follow this step. So since we know it's exponential, it's going to be in the form of a times b to the x. And we just have to find little a and little b. That's our job. So a is just the initial value when x equals 0. So in this case, you can see when x is 0, y is 8. That's the output of the function. And so 8 is little a. So we've already got part of it. Now we need little b. So to find little b, it's the number each y value is multiplied by to get to the next one. X has to go by ones though, so be careful with that. But to get from 128 to 32, I would multiply by 1/4. You might think of dividing by 4, but remember that dividing is the same as multiplying by the reciprocal. Then to get from 32 to 8 is going to be 1/4. 8 to 2 is going to be 1/4, and so on. So you see how this multiple is constant? That is your little b. So in this case, b is going to be 1/4. So our function is just 8 times 1/4 to the x. Bada boom, bada bing. Think it's going to be complicated? Not so shabby, not so shabby at all. Let's get into some applications. This is why you learn exponential functions and logarithms. Our population grows at a certain rate. And to set this up, we're going to have this relationship. This p equals p sub 0 times the quantity 1 plus r to the t. This is a formula for population growth. And when I look at this, if I see this p sub 0, that is the initial population. P is the population given a certain time. Notice our exponent is time. That's going to be your variable, and that's the thing people always want to find out about. Then p sub 0 is our initial population, and r is the growth rate. R is negative if you have a decreasing population. You have something decreasing exponentially. The rate is going to be negative, and this base right here is going to be less than 1. That would be a decrease. T stands for time. Now let's look at radioactive decay. You might remember Times Beach here in St. Louis. This is the radioactive decay formula. It's also called the half-life formula. You have S equals S sub 0 times 1/2 to the T over K. If you know what everything means, these formulas are a snap. So S is going to be the amount of a substance at time T. S sub 0 is the initial amount of substance. If you get used to these little sub-zero things, it'll make your life easy. That's always something that starts out. It's the initial value. It's the starting value. 1/2 is, of course, 1/2 because it's a decreasing at a rate of 50%. 1 minus 0.5 is where the 1/2 comes from. T is time, and K is the half-life. This will be important when we get to the archaeological dig project, if we do the archaeological dig project in that. It's kind of interesting. Be careful about time and half-life. They have to be the same unit of time. So you can't have 5 years and the half-life be 3 seconds. You have to make sure these match up. If this is in years, then the half-life has to be in years. If this is in days, then the half-life has to be in days, and so on. So be careful on those. Let's apply these to some word problems. The population P of a town of 475,000 is increasing at a rate of 3.75 each year. Find an algebraic representation for P as a function of time. When will the population be 1 million? This is the kind of thing people want to know. Do we need to build new hospitals? Do we need to build new roads? This is how we figure it out. So let's start with our formula. P equals P sub 0, 1 plus R to the T. And really, you only have a couple things you have to pick out here. So right away, I get 475. That's our initial population. I plug that in for P sub 0. The rate is 3.75%, and it's going to be plugged in for R. We don't know T because we're being asked how long. So when we set this up, here's what we'd have. 475,000 times the quantity 1 plus 0.0375 to the T. You can write this 1.0375 to the T if you like. When I would do this, since we don't know logarithms yet, or we're going to pretend you don't know logarithms yet, population, when it reaches 1 million, we're going to put that into y sub 2 on our graphing calculators and figure out where those graphs intersect. So if you put y sub 2 is 1 million, that's a 1 followed by 6 zeros, put this equation in for y1 and see where they intersect. So here's what your calculator would look like on the window from negative 130 by negative 1 to 1. I did 1.2 million. 1,200,000, and notice they intersect right here. That is how you're going to be solving exponential equations right now at this time. So this point is 20.19, 1 million. So the question was, when will the population be 1 million? You have to remember what is your x and what is your y. Since x is the time, your t is going to be approximately 20.2 years, and that's how you'd answer it. So not too shabby for these. All right, so let's look at one where the rate is decreasing and how we set this up. Population P is 123,000 and decreasing at a rate of 2.375 each year. Find an algebraic representation for P as a function of time. When will it be 50,000? So see if you can set this up. Pause the video for a minute and see if you can set up the function and solve it. All right, let's see how you did. So P equals P sub 0, 1 plus r to the t is our formula. If you write it, you'll get it memorized. If you write it every time you use it, you get that formula memorized. So P sub 0 is our initial population. That's going to be 123,000. Since it says decreasing at a rate of 2.375, we subtract it. So we're going to have 1 minus 0.02375, and that's all going to be raised to the t. In our calculator, we use x. It's fine. y1, this is what we would put in for y1. And y2 is going to be 50,000. So when we plot those in our graphing calculator, this is what we're going to get. And notice that this is decreasing. The red graph is your exponential function, and the purple line there is your horizontal line. Where they intersect is the solution. Remember that x represents time, so our answer is 37.45 years from now. So in approximately 37.45 years. All right, now we're going into to radioactive substances and half-life. Half-life of a certain radioactive substance is 2.5 seconds, and S represents the amount of the substance initially. How much of the substance is left after 2.5 seconds? Well, that's easy, half of it. After 5 seconds, half of a half, and so on. So that's our half-life, 2.5 seconds, and that would represent K in our formula. And if we're doing what they want us to do, they want us to take it a little at a time. So we'd have our initial substance times 1/2 to the first power, because we'd only have one half-life done. After 5 seconds, you'd have 1/2 times 1/2. In t seconds, we would use our formula, the substance times 1/2 to t over 2.5. So this is pretty much where I would start. Your book sometimes asks you to look at the pattern and do the logic first before the equation. They want you to see why you do t divided by 2.5. Because if half of the substance is left after 2.5 seconds, then it would just be half times what you initially started with. Well, how do you put that? Well, that'd be 2.5 over 2.5, because it's 2.5 seconds. Then the second one would be a half of that, so it'd be your substance times a half times a half, so it's S times 1/2 squared. And that would be 5 over 2.5, which would give you the 2 here. So they're trying to kind of show you where this formula comes from. That's why they ask it in kind of a funky way. So let's sketch a graph and see if there are 4 grams of the substance initially. So let's take a look. I'm going to put this in as y1 times 1/2, up arrow, x divided by 2.5. Now make sure you put parentheses in your graphing calculator when you put that in. My window, this is just a suggestion, -110 by -1.5. So let's go ahead and graph that. So there it is. There's what the graph looks like. They curve down. They go one direction. They're either increasing all the way or decreasing all the way. You notice it's going to get closer and closer to 0 without ever actually getting there. All right, what is the initial amount of the substance needed if there is to be 1 gram left after 1 minute? Well, let's plug in what we know into our formula. So initially, we don't know that one. We know there's 1 gram left after 1 minute, so we're going to put that in as S, because that's the amount of substance left at time t, and 1 minute is t. Now here's where it gets, you have to remember they have to be in the same unit of time. So we're going to put 60 seconds in for t instead of 1 minute. Since half-life is in seconds, we must convert 1 minute to 60 seconds. So t is going to equal 60 there. So when we plug this in, here's what we end up with. 1 equals initial amount times 0.5 to the 24th. To solve for this, we would divide both sides by 0.5 to the 24th power. So here's what we'd end up with. 16,717,216 grams. Pretty big. Exponential functions get very big very fast. All right, that's it. I just wanted to give you a brief introduction to exponential function, and I will see you later.